the 14th lecture in the course Optimization and Data Science. The topic of this lecture are Basics of Stochastics and Statistics. So I will talk about random events, random numbers, random variables as the basis of statistics, then about probabilities, about some parameters of probabilities and probability distributions, expectation, variance and covariance, and at the end then about random samples. So this is the beginning of the part on statistics, and we will continue this also in the next lecture. Yeah, so stochastic and statistics, of course, it's an important area in mathematics, but for data science it provides theories and methods that we can use for data analysis. And we can always regard data as results of random events. And this is the basis of all statistic analysis of data. It might be measurement data, also simulation data, whatever. Yeah, and we need to understand the notions of random variables, probabilities, and then we can determine or estimate parameters of given data. We can use this to analyze the data, to detect typical behavior and also outliers in data, and we obtain tools to decide if data support a certain hypothesis, and we can also quantify uncertainties. So in this lecture we start from the basics, and we start now from with the term random. And the basis is to consider a random process. And I want to describe this by giving some examples, very easy examples. So rolling dice can be considered as a random process, or randomly picking one picture out of a database, or just choosing one index out of an index set. We can all see these events or these actions as a random process. And the result of a random process is called a random event. And again, if dice shows one specific picture is taken or is picked out of the database, or one index is chosen, this is then a random event. By omega we denote the set of all possible events. And for example, for dice it's just the numbers, or they can be identified with the numbers from 1 to 6. Can be all pictures in the database, or which can be again identified just with indices, or this set can consist of an index set itself. And this set of all possible events might be discrete, or it might be continuous. A random variable is a mapping now from this set of all possible random events to the real number, to the set of real numbers. So from omega to r. So it's a function. Every event is associated with the result of this random variable. A random vector is just a vector of random variables, and the main difference now here that we have to know is the random variable in contrast to its realization. So if we consider one fixed random event out of the set of all possible events, the mapping then, or the value of the random variable then, is the realization of the random variable. And the random variable is often denoted by capital letters, and the realization done then by lowercase letters. So in the example, throwing 2 dice is a random event, and mapping a throw onto the sum of the numbers the dice show, this is a random variable. And if we actually throw the dice and they show certain numbers, the sum of these numbers that are actually shown, this is the realization of the random variable. Okay. And for random variables, we can, rolling 1 dice, we can just take the value obtained is a random variable. The pair of 2 dice that we roll of both values is a 2-dimensional random vector. If we take the sum of both values, we have again a random variable. And for the example with pictures, we can define omega as the set of all possible choices to take one picture out of a finite set of pictures with either cats or dogs, or simplify just the finite set of pictures with cats and dogs. This can be, if this is the set of all possible events, then the mapping might be the random variable that we take 0 as a result if there's a cat on the picture and 1 if there's a dog. This is a random variable. It has only values in 0, 1, but these are also real numbers, so it's a subset. The distinction between a discrete and a continuous random variable. A random variable is called discrete if it attains only countably many values. So if we can index all possible results of the random variable, if we can numerate them by xk, and k is an integer number. If the set omega of all possible events is finite itself, or if it's countably infinite, then x is a discrete random variable in any case. For example, these two sets here from the last example, 0, 1, and also 1, 2, 3, 4, 5, 6, they are finite and obviously countable. But also these infinite sets, n, z, and q, they are countably infinite. All examples above were discrete random variables because the results that were possible are all finite in all 4 examples. In contrast, a random variable is called continuous if it may attain uncountably many values. And this depends on the set also of all admissible or possible events. If this set is countably infinite, then x might be a discrete or a continuous random variable. And for example, if we have a set of all possible events which is r or rn, or intervals on the real line, or higher dimensional Cartesian products of intervals, these sets are uncountably infinite, but it still depends how many values the random variable might attain, if the random variable is discrete or continuous. One way where a random variable is very important or often used is, of course, a random number generator. If we want to somehow model or generate random numbers on the computer, there's a simple way to do this, but this is in fact a pseudo-random generator, because it's obviously this is a deterministic formula using the modulo function with some parameters and some given random seed. This is a deterministic sequence, and also if the random seed is taken randomly, then only then we can say this is the realization of a random variable, and the result is always in 0, 1. So this would be a continuous random variable. On the computer, the A0 is usually not taken completely randomly. It's just a pseudo-random number using the system clock or something like this. Then obviously we don't have a random variable, and that's the reason why this is called a pseudo-random number. Even if A0 is random, on the computer we can only attain here countably many values, because these are the machine numbers. However, this formula here, this algorithm, is taken as a random number generator because it's a model or an approximation of a continuous random variable. This means we take this algorithm or this formula to generate numbers in 0, 1 and consider them to be on the continuous interval, even though this is not true, because we know we only have the machine numbers in floating point representation on the computer. Between random events and random variables and data science. The point is that in data science we often regard the given data as realizations of a random variable. For measurement results or measurement data, this is more or less obvious, because usually these data contain measurement errors which are in some kind random or which are considered to be random. Data from unknown or not exactly known processes are also considered as being random data or results of random variables. And so, for example, data from social behavior, from experiments, medical, biological, pharmaceutical experiments, and also natural phenomena, for example, weather. If we look at our simple example of rolling dice, there are clear physical laws that determine this process, and the same is for weather, or from obviously also for medical, biological processes that are going on. But the dependency on parameters is very high. For the dice, it's the position or the direction of the throwing, the velocity. This is very complicated to model or to observe, to determine these parameters, and then an exact computation is nearly impossible. And this is thus modeled as a random variable. And so main processes that we consider to be random, they are not random in fact, because real random processes in nature are very rare. For example, radioactive decay is one of them, but most of the data that we take is not from these kind of processes that are really random, but we consider them to be random, because it's the easiest way if we don't have an exact model, because it's difficult to obtain a model just for social behavior or from biological processes, for example in the human body, and or for some drugs that is used in experiments. So we use statistical analysis and consider the data as being random. Okay, so after we have the random terminology, random events, random variables, we come to probabilities. On this slide there is a mathematical assumption that we need for the set of events. This is somehow then quite natural, but I want to state this result because it's necessary to exactly define what the probability is. And this is a definition of the system of sets, and it's called sigma algebra. So omega is again our set of all possible events, and we consider now a system of subsets, which is this A here, and it's a part of the power set of omega, and we require three things. So the whole set omega must be in this set of sets or systems of sets. If one set is in this system, also the complement has to be in it. So the empty set, of course, has to be part of this sigma algebra, because omega is also inside the complement of omega with respect to itself. It's the empty set. And the third thing is the most important one. If we have a number, countably many subsets, then the union of these subsets has also to be a member of the system of sets. It's always possible to generate a very trivial sigma algebra on omega, just taking omega itself, satisfying the first, and the empty set, which is necessary because of the second one. And obviously we only have two sets then, and if we combine them we have omega again, and omega is in A. So this trivial sigma algebra satisfies the definition. On the other hand, we can always take the power set itself, and it's also a sigma algebra because it contains all possible subsets, and then we can also verify the three conditions. And here for rolling the dice, this is just can be made very clear that we have here these two sets would be empty set, and the whole omega is then, we can use this as sigma algebra. But usually if we really consider rolling dice as a random event and then take random variables, for example the value that is shown, then we would use the power set as sigma algebra. And here we can see if I take 1 into the sigma algebra, I have to take the complement of the set 1 here inside, and the same is if I take 1, 2 inside, I also have to take this set inside. And if I take the whole set inside, I also have to take the empty set, and so on. So we have all, it's clear that we need all possible subsets. And the second one, of course, is more appropriate for random. The second main notion that we need is probability measures. And in fact, the sigma algebra was just needed to define the probability or probability measure in an exact way. So we have a sigma algebra, so this A is a system of subsets of omega, and then a mapping that maps any of these elements of this, so any subset of omega which is in this sigma algebra on a number between 0 and 1 is called a probability measure if these two conditions are satisfied. For the whole set of admissible or possible random events, we have to get the probability of 1. And then if we take the union of sets with empty intersection, so a countable union, then we can add up the probabilities of these elements of the sigma algebra. This is the rule that has to be satisfied. If the two sets or more sets are have an empty intersection, we must add up the probabilities of the different subsets. If we take again the example of the dice and we have the trivial sigma algebra, we can just define the probability of the empty set is 0 and the probability of the whole set 1 to 6 is 1. So the probability to obtain one element out of this set is obviously 1. And so this is trivial and does not make sense or gives it's not very useful for application. If we take the other sigma algebra, which is the power set, and we set the probability of every set with just one element to 1 over 6, and then apply this rule 2, then we get what we usually consider as reasonable if the dice are not manipulated. So the probability to obtain one number in this set, 1, 2, is obviously the probability of obtaining the 1 and the 2, which is 1 over 6 plus 1 over 6, it's 1 over 3. So this then obeys this rule and then obviously is a probability measure, and it's consistent with our intuition, what we want to have for this very simple example. Now we come to probabilities that are associated with discrete random variables. So as we had a random variable which is discrete can only attain countably many values, xk, and we denote the probability that the random variable attains one value just by this p of capital X equals lowercase x, and we call this function here, which sums up all probabilities lower than this given number here, this argument, we call this function the cumulative distribution function of x. And the example with dice is quite obvious. We already had these probabilities 1 over 6, and then it's clear, for example, if the probability to obtain values lower or equal to 2, which is then probability of 1, or plus the probability of 2, is 1 over 3. If we take the sum of two dice, we can also do this. Then the computation gets a little bit more complicated. If we say the set of events is then this here, all pairs that are possible, the sigma algebra is also the power set, And the random variable can be defined like this. We take omega 1 and omega 2, and the result of the random variable is then the sum. We can easily compute here what we have as probability. So the probability to obtain a 2 is 1 over 36. Same for the probability to obtain a pair of 6. And so on and so on. You can stop the tape and look at this formula, and it's obvious that they are true. For continuous random variables, the definition of the probability is usually done by using the probability density function, PDF, usually denoted by lowercase f. Since we have a continuous random variable, by definition it may take infinitely many values and uncountably infinite many values. This means we can use the horizontal axis to represent all the values that the random variable might take. For example, here it's a whole real line, or I just depicted here part of the whole real line, maybe just an interval -2 to 2, and then the probability density function is used to describe and to define the probability in the following way. If we want to have the probability that the random variable attains values between a and b, we take the integral from a to b over the probability density function. Here's an example, this red set here, so this area here describes the probability that this random variable attains values between -1 and -0.5. We can see here the probability density function of a Gaussian distribution, which we discuss later in the next lecture. Obviously, the probability density function has to have non-negative values, and it describes the density in some area of the values that the random variable might take. It's the probability that the random variable just attains one value, for example here the value 0.5, is always 0 by this definition, because here is only defined for an interval, not for a single point. Or you can see if you set here a equal b, you get here an integral over just one point, which in mathematics is always 0. So we cannot talk about the probability of a random variable being equal to some value. This makes no sense for continuous random variables. And it's also obvious that the integral over the whole real line of a density function always has to be 1, because then we would get here p of all that the random variable attains any possible value, and this probability has to be 1 by definition of the probability measure that p should be. So this is the main quantity, the function, the PDF. It's used to describe the distribution or the probabilities of continuous random variables. The second function that is used is the cumulative distribution function, or CDF. The CDF is the counterpart to the definition of the discrete random variables, because it's the value of this capital F here of x is the probability that the random variables attain values lower or equal to x. And it's just the integral from -infinity to x of the density function. And here we see the example. If we have this probability density function, you see it's always non-negative, and the integral is a non-decreasing function, because it sums up or integrates the area below this curve. And you can see here, then here it's growing, and then it's nearly 1. So the limit of the distribution function, if we go to 0, if we go to -infinity, has to be 0, and if we tend here with x to +infinity, it has to be 1. So it always has this behavior. And now we can take here, we can evaluate this cumulative distribution function at one point, and the value that we obtain, the result gives us the probability that the random variable attains values that are lower or equal this point here, this value here. Okay, we come now to main parameters of random variables, which are expectation, variance, and covariance. So the expectation is the value that we expect as an average if we have a high number of realizations of a random variable. And defined is it in the following way. The notation is using here this E. Sometimes a normal capital E is used. Sometimes also here rectangular brackets or even no brackets are used for the expectation or expected value. This is different in different books, or different people use a little bit different notation, but it's always the expectation. For a discrete random variable, we just multiply the value that the random variable might take. They are countably many here. The value that the random variable might take multiplied by the probability that it attains this value. For a continuous random variable, we cannot sum up because we have uncountably many values that the random variable might take. We take the integral from -infinity to infinity, or the integral over r x. So the value that the random variable might take multiplied by the value of the density function. And for vectors and matrices of random variables, the expectation is just defined component-wise. So as I said, the expectation is something what we expect if we perform a high number of realization as an average. The expectation is linear, which can be easily seen here because the sum is linear and also the integral is linear. For random variables, we can and the factor a, we can compute it, the sum, like this. And this is also a property of the integral, or the sum, and the probability. Yeah, as example, we take again the dice. So if we roll the dice and just take the value that we see as random variable, then we can see every number has the same probability, 1/6. So we can sum up the value of the random variable 1 times 1/6, and then the other values all multiplied by 1/6. So we get this, and we get 7/2, which is 3.5, and this is the average that we expect. We would expect something between 1 and 6, and in the middle, which is 3.5. If we take the sum of two dice, then we have these probabilities. They were on some slide before. Yeah, we can do the same calculation here. We have the value of the random variable times its probability, and if we sum all this up, we get the value of 7, which is also what we would expect in the mean. And can also be computed by the linearity of the expectation, because it just gives 2 times this here. So summing up 2 random variables x and y, which have both this expectation here. Yeah, for the uniform random generator on the 0, 1, we can do this by computing the integral. And a uniform random number generator has the same probability density function on the set, on the interval 0, 1, and the value then has to be 1, because remember, the integral of the density function itself has to be 1, and so the probability density function of the uniform number generator is 1, so we get just this integral here, and the value is 1/2, which is also natural. For a uniform random number generator on 0, 1, we would expect in the average getting a 0.5 as value. Second main parameter of a random variable is the variance. And the variance is the expectation of the squared difference of the value and its expectation. So an average deviation of x from its expectation if we perform a high number of realization. In formula it's like this, and there is the v is used, or also the VAR is used as abbreviation for the variance, and it's defined, we take the value of the random variable minus its expectation, we square this and take the expectation of the result. And this is also called the second-centered moment. So in general, if we take the expectation of x to the power of k, this is called the kth moment. And if we compute the kth moment of x minus expectation of x, then we call this moment centered. It's centered around the expectation. So it's somehow the deviation of the random variable from its expectation, and then to the power of k, and then again the expectation of this. So we can consider this as the average. Okay, if we do this, you can do now computations which, even for the simple example, we have to compute a little bit. If we have the rolling 1 dice, the expectation is 7/2, and we have to compute the expectation of this square here then, which gives a sum again. The values that we get is from 1 to 6, and then we have to take always the value that the random variable might attain. So starting from 1 going to 6, always minus the expectation, square all this, sum them up, and 1/6 is also the parameter of what's the probability that the 1 is attained, or the 2 is attained, or the 6 is attained. So we have this common factor here, 1/6, and this is a computation that can be done, and we get 35/12. So the variance is nearly 3 of rolling a dice. But remember, this is the squared deviation that we expect. So the squared deviation of the random variable to its expectation. And therefore this number gets big here because the differences are all bigger, or most of them are bigger than 1 that we compute here. We can do the same thing for the sum of 2 dice, and this is already a little bit longer. So if you want to compute this, if you want to do an exercise, you can do this now on your own and stop the tape, take a sheet of paper, try to compute it. I show the result in some seconds. It is obtained very easily just inserting, but it's a little bit longer computation. So we again have to take the expectation of the difference here of the values that the random variable might attain, and this started from 2 to 12. So we compute always 2 minus 7, 3 minus 7, 4 minus 7, and so on until 12 minus 7, squared always, and then multiplied by the probability that the 2 is obtained. And for 2, we had this on some slides before, that there was always the common factor 1/36. To obtain a 2 is just, the probability was just 1 divided by 36. To obtain a 3, there were 2 options, and so on and so on. It's the number of options that there were is growing here, and then it's going down again. And the probability to obtain a 12 is only 1 if we have 6 and 6, and then we have again the probability 1 divided by 36. Computing all this, we get 35/6 for the deviation, which is basically 6. And again, the reason why this number is big, that we always compute here the square of the deviation. So, and because the deviation here is in most cases it's bigger than 1, by taking the square we get a big number because it's a quadratic deviation here. For the uniform random number generator we have the expectation 1 over 2. Then we have to compute an integral, and yeah, we compute here the integral, and again the density function is just 1 on this interval and 0 outside this interval, so we have to compute this integral here, and then we get 1 over 12 for the variance. And here the variance is comparably small because we only have values between 0 and 1, and squaring them gives smaller values. The next important term is the covariance and the covariance matrix of random variables. So if we have 2 or more random variables, the covariance is defined as the expectation of this product. So if we have 2 random variables, it's just we take the product of x minus the expectation and y minus its expectation, multiply this and take then the expectation. And we do the same thing for if we have a random vector, we then define a covariance matrix, which is then defined by all possible covariances. And on the diagonal you can see easily if we set here x equal to y, we get here just the variance. So the diagonal of the covariance matrix contains the variance. And so the covariance describes independence of random variables, and as a result or a consequence, the independence of random variables is defined by the covariance. If the covariance is 0 between 2 random variables, then they are defined as independent, and if we have more, they're called mutually independent if all the covariances are 0 for different indices, of course. Similar way or related to the covariance, we can define the correlation of random variables. So if we have 2 random variables, the correlation is just the normalized covariance. So we divide the covariance by the square root of the product of the 2 variances. And thus we get values between -1 and 1. And if we compute the correlation between the same, so between x and x, we can see that we get a 1 here because the covariance x, x is just the variance, and then this cancels out. And this means for the correlation matrix, where we also here use the division of the 2 variances, we get a 1 on the diagonal. And for the other values, we get values between -1 and 1. And we call random variables uncorrelated if their correlation is 0. And we also use the term negative correlation for values which are lower 0, and positive correlated for values which are greater than 0. If 2 random variables are positive correlated, this means if one grows, also the other grows. And if one is getting smaller, also the other is getting smaller. If they are negative correlated, then if one becomes bigger, the other one becomes smaller, and vice versa. Consider rules for the variance and also for the covariance afterwards. So for the variance, we can use the linearity of the expectation to compute the variance if we multiply the random variable by a factor alpha, or if we take the sum of 2 random variables. And all the red terms here are the terms where I use the linearity of the expectation, and here it's very easy that I can put out the alpha here. Then I get here, I can put out the alpha out of this bracket and get an alpha squared. Again, with the linearity of the expectation, I take this out and I get alpha squared, the variance of x, if I multiply here the random variable with the factors. And it's clear because in the variance we always have the quadratic deviation here and then the expectation of it. So we get an alpha squared. For the sum, we do the same thing. We split here the inner bracket, we just write it in this way. And then we compute here evaluate the inner quadratic term to get this. again use the linearity of the expectation. We get 3 expectations here a mixed term, and the first and the last term gives just the variance of x and y, and the midterm is just the definition of the covariance. And if we look at rolling a dice, we see that we consider this as a the sum of 2 independent throws. We consider the throws as being independent, and the definition of independent was that the covariance is 0, so we just get the sum of the 2 variances, which we already computed this for 1 dice, and for 2 we also computed this, and this corresponds with this formula or this computation rule. For the covariance, it's often used if we have a covariance matrix then, or we have a random vector here, and we have a matrix, so we multiply the random vector or the random variable here, the vector of random variables, by a matrix A, then we see that we get here an A and an A transposed on the right hand side, and then the covariance of the random vector. And this can be also computed easily by just putting it in. That's the definition of the covariance here. This is the covariance between xi and xj, and the matrix is just built by computing all these terms for ij from 1 to n. And we defined the expectation of a matrix by just by computing the expectation of every element, and that's what we use here. So the expectation of the matrix is the same thing as the matrix of expectations. And what we see here inside, we have here now a matrix inside this outer bracket, and this is just a dyadic matrix product that we already had. We can write it like this. So the covariance of x can also be written like this. And again, we use the linearity of the expectation to take out the matrix A outside this expectation, and the same here. But then we have here, again in the second term, here we have the transposed. So we transpose this difference here, which gives the changed order and both transposed. So we have here x minus e of x transposed, which is a matrix. Which is a vector, sorry. X is a vector, e of x is a vector, this is a vector, and this is a matrix. And here we already see that we have an A here coming from this first term, and here in the second we get an A transposed. And if we look at the inner part, and then we have 2 matrices multiplied, we can use again the linearity of the expectation, that the A can be taken out of the expectation, and on the other side also the A transpose. We get this here, and the red term is now the covariance of x, which we already had here. And this gives this formula, which is important for random vectors that are transformed by a linear transformation. And so this is the way how the covariance is changed. I want to introduce finally is the one that we need when we consider data and want to do a statistical analysis, is the term of random samples or just samples. So if we have a set of random variables that are mutually independent, so their pairwise correlation or covariance is 0, and if they have the same distribution, so this means the same cumulative distribution function, or for a continuous random variable the same density function, then this set of random variables is called a random sample, or they are called IID, which means independent and identically distributed. So for example, if we have as random variable the age of the students in the course, and we take now out 10 students out of the group, then we have a random sample. Or if we have the measurement of temperature at some location in the ocean at some given time and in the day, and then we're taking measurements at a number of days, this is then a random sample. We will use this term in the next lecture, where we go deeper into the stochastics and statistics and apply it on data science. So important now is we had the main terminology. So a random event is an event that is regarded as being non-deterministic. The result of a random event cannot only be predicted.